Okay, in this next section, we're going to look at free body diagrams and combining forces. So we're still in section 1, and this is lesson 2. A free body diagram is one that shows all the forces acting on an object. Let's consider the forces that are acting on a man as he pushes the car. So if we look at this person over here, as he's pushing the car, there are several forces that are acting upon it. First, we have a force that's being applied. Now, the car is going to resist the movement, so we have force applied here. But we also have friction resisting force, and that's due to from the pavement. So we also have a force of friction. And there are two other less obvious forces. We have a force of gravity, which is pulling the car into the ground. Now, since the car is sinking into the ground's also exerting a force resisting gravity up, and we call that normal force. So if we look here, a free body diagram, which is what we have shown, is a simple way of showing all the forces that are acting on an object. So we have the force that's being applied, that's the man pushing the car. In the opposite direction is the force of friction. We also have the force of gravity, which is pulling the car down. And we have the normal force, which is resisting gravity. So in most cases, all forces point outwards from the object, and they're seen to act from the center of the object. So what we have drawn here, that would represent the center of the car. So if we drew the car in here, so it's acting from the car's center mass. Okay, another example. We have a sailboat showing all the forces acting on it as wind blows and pushes it through the water. So we have the force of the wind here. So our F1, what we just noted as the first force, is the wind blowing and pushing the boat forward. Well, what's resisting the movement of the wind here would be the drag or friction between the boat and the water. If you want to think of this force, every year most fishermen would take their boats out of the water and remove any barnacles or debris that's built up on the bottom of the boat because it costs extra fuel because of the drag. Many large oil tankers go through that once or twice a year. There's the force of gravity, which pulls the boat down into the water. So that's our force here. And we have the normal force, or buoyancy force in this case. And if that wasn't there, then the boat would sink. And our free body diagram here would represent each of those forces. So the normal force pulling the boat forward, force of friction or drag slowing the boat down, our force of gravity pulling the boat down, and then our normal force, which is pulling, not pulling, sorry, but pushing the boat up, providing it with buoyancy. Next, we have a free body diagram representing an object being pulled across the table at a constant speed. So that's important here in this example, that's being pulled at a constant speed. So we have a force of friction resisting the movement. We have the force that's being applied, the pulling force. So we sometimes call that, or we will call that, the force applied. We have a force of gravity here pulling it down. So Fg, and these are subscripts, so it has to be written lower than the capital F. So that's pulling the object to the table. And since the object doesn't go into or through the table, we have a normal force that's pushing up. And what we want here is to get the net force or overall force of an object. So the net force is the sum of all objects acting on it. Linear forces are those acting in a straight line. So we'll consider those forces acting west-east, and we'll also consider the forces acting north-south. Now these linear forces can be added arithmetically. In other words, we'll just use math to add the forces. And we'll consider each of them separately. So we'll consider the east-west forces and then the north-south. So we look from east to west and after north to south. Above, the up-down forces must be equal in this case, since the object does not move vertically. So in our example here, we're just pulling the object across the table. The force of gravity is balanced with a normal force resisting it. Since it's not floating off the table or going into the table, these two forces, the downward and the upward motion, must be equal to each other. Now, since the object is being pulled forward, it's overcoming friction. So the force applied must be just a little bit greater than the force of friction. Okay, now we'll move on to our next example here. We can have a chance to try this out. Okay, here's an example for you folks to do. Example 1, a 50 kilogram box is being pulled horizontally across the floor with a 1200 Newton force. When a frictional force of 15 newtons opposes the motion. So part A, draw a free body diagram showing all the forces that act on the box. And after you have that completed, what would be the results of the applied and friction force when combined? So find the net force, is what we want there. And force is a vector, so that you may need to keep that in mind when considering symbols. Okay, I assume most of you were able to put in the force applied of 1200 newtons. Our frictional force acting in the opposite direction of 15 newtons. But how many people consider the force of gravity and the normal force? So what you have to remember, the force of gravity is the mass times gravitational constant, or 50 kilograms times 9.8, which is going to be 490 newtons. Now, since the object isn't sinking into the floor, the normal force, or the force exerted by the floor to hold it up, must be equal to that. Okay, now part B, what's the net force? And we're only considering the applied and frictional force. So force net, remember this is a vector. We have 120 newtons, or the force applied. And since they're in opposite directions, we're going to subtract the frictional force. Now the net force is 105 newtons. And since direction wasn't given, we'll just assume that instead of saying east, we'll say it's to the right. But if you said east, will be just as fine, since force was not given, or direction wasn't given. Okay, before I get into the next section, I'm going to end this video here now, and then I want you to play the next one. Okay, we're going to continue with the same lesson. Next part, combining forces. All the separate forces that act on an object can be combined. The resulting forces can be called unbalanced force, symbol there, force unbalanced, net force, or resultant force. We're going to refer to it as the net force. Okay, there. So the net force would be the single force which could do the same job as all the applied forces combined. So in the next couple of questions, we're going to look at all these different forces acting on them, and then bring it down to only one force that would act on an object. So instead of there being 3 or 4 different forces which act on an object, how could we combine them into one force that could act? And should note that both the size and direction of this force are important. So this is a vector. Later in the unit, we'll see the forces can be combined using either a scale diagram approach or a mathematical approach. Okay, different cases of combining forces, and there's 4 cases in which a force can be combined. Number 1, we can have 2 forces that act in the same direction, and when we have 2 forces that act in the same direction, we'll just add them together. So here force 1 is pulling at 120 newtons, force 2 at 80, so then the net force, and this is a vector, would be adding both of these together. So you would have 200 newtons. In this case, we'll say it's moving to the right. Next, forces could act in the opposite direction. So force 1 is pulling at 120 newtons, and then we have a force resisting that motion at 80 newtons. So our net force is 120 newtons. Subtract the 80 because it's in the opposite direction. And then we have 40 newtons. And instead of saying to the right, we'll say it's acting to the east. Now if you wrote down 40 newtons to the right, that would be okay so long as a direction wasn't specified. Okay, next example. Forces could be perpendicular to one another. So in this case, forces are acting at 90 degrees to each other. So if you forget what perpendicular is, it would mean that two forces would act at 90 degrees. So if we just think of it this way, since they're acting from the middle of an object, they have to be at 90 degrees. This is going to be very similar to how we handled vectors in the last chapter. So I'm going to pause the video. When we come back, we'll have the solution there. So take a moment and try and figure it out on your own. Okay, so to summarize this, we have a force 1 going down, or in this case we'll specify south, and we have force 2 which is pulling to the east. So over here we can use a vector diagram. So the force pulling down and then across. So remember when you're adding your vectors, it's head of the first to tail of the last. So we put our two vectors in here, just same as we did in the last chapter. We want to find this one here, our net result. So since these forces are at 90 degrees, Pythagoras' theorem would apply. So we have a squared plus b squared equals c squared, or 120 squared plus 80 squared equals c squared. So c squared will be 20,800, and then take square root of that number, and we get 144. Now we're going to concentrate a little more in this section on the significant digits. So here we only have 2 will be our lowest. So we'll round that answer to 140 newtons. Now remember, we also said that this had direction, so we need to find that angle. So don't write in or assume that your force net is going to be 140 newtons. That's half the answer. We also need to have the direction in there. So to find this angle here. So since you have the opposite side and adjacent, so this is 80 and that one's 120, we can use tan. So theta would be the inverse of tan, 80 over 120. Same as last chapter, so this will be second nature now. And our angle will work out to give us 34 degrees. And describing this motion, so the first force is going south, that's going 34 degrees east. So your final answer is south, 34 degrees east. Next one. The fourth way which force can act is that the forces are not perpendicular at all, and we'll examine that later. So again, quick review back. We have forces in the same direction. They can act in opposite directions. They could act perpendicular to one another, Or we'll have cases where they're not going to be perpendicular at all and just acting at different angles. So I want you to complete this next example. And forces are perpendicular, and there's multiple forces in this case going on. So find the net force acting on the objects. And when you're doing this, remember to do these in pairs. So do those that are north-south, and then combine the forces that are west-east. That'll bring it down to a problem where you only have two forces that you need to resolve. So don't forget north, south, west, and east.